So hi everyone. So I will present a robust analysis with MOODD components, MOODD for monitoring online and operational domain design. So I have to say I'm not part of the MOODD conception team, but I can present my colleague works. So what is MOODD? So MOODD is a component for analyze the model robustness related to a specified ODD condition. What is an ODD condition? It's an information related to operational domain of an AI-based system, like task information, data, or metadata characteristic, which are likely to play an important role and have a strong impact on a model. There is several kind of ODD conditions. Some are more data-based. For example, we can think about blur or brightness on a computer vision problem. Some are more mathematical based, like noise or adversarial issue. And some are more industrial or operational based, like some information about location or sensor specificities. So here we want for a trained model using a pair of quantifier and generator related to the ODD conditions that we want to study. MOODD will perform a comparative performance analysis on samples which are transformed by the generator to analyze the impact of such ODD condition. So the global purpose of MOODD is to analyze and evaluate model or AI component behavior for a range of specified ODD parameters in a bottom-up approach, which means from data and model weakness to specification. Then it can be useful to confront the business ODD parameters, which are identified in more top-down approach, which means from expert knowledge to specification. Then it can be interesting to, if we find some model weakness thanks to such analysis, try to mitigate such model weakness by performing, for example, calibration of detector that can trigger alarm when inputs are close or outside of the identified model ODD limits. So, quick illustration to illustrate that business-driven ODD can sometimes differ from an empirical model ODD, which means the area where the model is effective. So on such image, for a specified ODD condition, for example, brightness, we can analyze the performance conditionally to the level of ODD condition. So we have here a sample which are slightly affected by the blur, and here the sample, the data which have a strong blur level. And we can see that the model performance will differ according to the level of blur. In a specified ODD, the business operator can want that the model have to perform in a specific area and have to face some blur level range. But if we analyze how much the model is robust to such area of modifying ODD condition, we can observe that our model is not robust at each location of the ODD area. And there is some area where the model doesn't meet the minimal performance that is required to use such model. So MOODD analysis can help to confront and to assess some model weakness. So when MOODD take place in the global methodological in the global Confiance.ai methodology. So there is 3 steps. The first steps come in the evaluation steps for evaluate rather the ML model or the ML components by performing evaluation of robustness to ODD condition. Then we can also be interested by refine an ODD specification or AI-based system by observe some empirical robustness, some lack of empirical robustness. And then there is a third part which take place in operation steps, where we can set up some tools for monitor, for example, sample according to calibrate threshold that are built to face some model weakness which are identified by such evaluation process. So now I will make a deep dive on the component and its utilization. And I can say that MOODD is a very simple component that can be seen as a pipeline of 4 steps. The first aim to generate new test sets related to the ODD condition to studies. And then we perform inference on this new test set. We perform evaluation of metric, and we synthesize and visualize the result to analyze the impact of the ODD condition on our model performance. So the MOODD pipeline will interact with the data and also model inference functionality. But sometimes we have to face some specificity of industrial use case. So MOODD have been designed in a modular way in order to incorporate some more specific implementation of such steps. Then MOODD can run as a Python script using function from the Python package or as a Docker controlled by Docker run commands or Airflow DAGs. So in the first steps, MOODD provides some transformation related to image, for example, rotation, translation, Gaussian blur, and to time series, for example, noise, missing value, offset. For the model running, MOODD is compatible with ONNX format and TF-Little's model, but it also runs on a Confiance use case with some more specific models as TensorFlow and PyTorch implementation. Then MOODD contains also some standard metrics in order to make image classification, semantic segmentation, or time series regression. And it provides some tools to compare and to visualize results of the degradation performance analysis. So, as I said before, MOODD is designed to be used when facing some industrial specificity on data or model. So we can use MOODD using the default pipeline with each generic steps, but we can also make some hybridation by skipping a generic steps and replace it by a specific implementation due, for example, here to a specific model inference API. And we can also execute each steps of the MOODD pipeline outside of the MOODD component and only use the MOODD analyzer in order to produce the graphical result of the analysis. So to utilize MOODD, we have to make some setup of configuration of the several objects which are involved in the MOODD pipeline. For example, model information, generator information, metrics information. And we have also to set up the experimental plan for the generation of the ODD condition to confront to model performance. Then MOODD run as simple as some command line. The first step will generate the new test set validation for ODD condition. Then the new test set will be used to run inference of the model. Then we compute metrics from this inference, and then we can analyze the result of our degradation performance analysis thanks to such kind of graph. And so I will now talk about the application of MOODD on 3 use cases of the Confiance.ai project. The first one is a Renault welding use case, which aims to build an AI-based system for assisting weld quality control. So more practically, we want to make a model to detect if welds are conform or not. You can see here some non-conform yield and some conform yield. So in such application, we have an ODD characterization. We have been produced by some industrial experts. So we have some ODD condition, and we can be interested to analyze the empirical impact of such ODD condition in order to analyze if there is some performance degradation according to it. And MOODD will provide some graphical results which can teach us how the model reacts to a specific ODD condition. So here for the blue motion horizontal ODD condition, we have an axis which characterize the sample with a very low level of blue motion. Here it's some image we have not been altered. And here some image with a strong level of blue motion since it have been altered by the generator. And we can observe the conditional performance of the model according to the level of blue transformation. And we can see here that the model is not robust to the such ODD condition because it have a strong degradation of performance when the blue transformation level is higher than the level 4. We can do the same analysis for other ODD condition. For example, here for the horizontal translation ODD condition. And here we can see that the horizontal translation have no impact on the model. So the model is kind of robust to such ODD condition. So we can, in operation, neglect such ODD condition, but we have to face to such ODD condition by make the model more robust or by set up some monitor process to handle the model weakness. So if we become to the analysis of ODD condition for the blue motion transformation, we can be interested by determine model ODD condition limit accorded to performance requirement. If we want a threshold performance of 0.8, we can be interested by have the limit expressed in a more usable indicator than the ODD transformation provided by the generator. So we can make the link and extract the information that if a new sample have an ODD measure, have a blur measure that is performed by a quantifier more than the 0.9 level, they are likely to induce a high risk of model error. So we can raise an alert that such a sample may lead to an increasing rate of model error. So we have done such process for several ODD conditions, and we identify some samples which are outside of model ODD limit according to MOODD analysis. For color ODD condition ODD, for a blur focus condition ODD, and for a blur motion condition ODD. Then we can pass to the second application, and here is a Thales Ariel use case where we want to make object detection in a high resolution view. So we want to detect some vehicle like plane, like large vehicle or small vehicle or boat. And the prediction, the boundary box detection, is done by a YOLO V5 which is applied on batch of the large view. So we can perform the same analysis of the impact of an ODD condition. Here we choose the brightness, and we can observe that the model is again not robust to the brightness condition. So for very dark image, the model have its performance which fall dramatically. And for images which are saturated in brightness, we also observe a slower but significant degradation of perturbation. So if we have to set up some ODD limits, we have to control that our batch is between a minimum and a maximum limit of brightness. And then we can apply it on each batch of our view in order to identify which are the batch which are related to high risk of model error due to ODD condition limits, exit of limits. And here, so for two images, we can see which batch are potentially or certainly out of the limits for brightness model ODD condition or for blur motion ODD condition. Such information can be used in order in operation in order to mitigate model weakness by performing some calibration or by assessing some increased risk of error. For example, here for an image which have some brightness issue, there is a boat and there is a boat which here is hardly visible. The YOLO V5 provide us some bounding box. And thanks to our ODD limit definition, we can add a new information to the bounding box. Here, the bounding box which are not filing, there is no issue. But when we file a bounding box with orange color, it means that there is a small risk of error due to some ODD condition which are close to the model ODD limits. And in red, there is an high risk due to several ODD conditions which exceed of the model ODD limits. We can also directly calibrate the model prediction confidence by take into account the fact that for the batch where we detect the bounding box, some ODD condition exceed of the model limits, so we can reduce the confidence level by performing some calibration process. The third use case application is close to the first one. So it's a Safran visual inspection where we want to make default detection on turbine blade. So we have again some conform image and some non-conform image. So such work have been done by the end-to-end Safran use case application team, which is totally independent of the MOODD conception team. And they tried to make an analysis of the score, which means the class probability predicted by the model, according to two ODD conditions, the brightness and the blur, and conditionally to the class. And from such analysis, we can learn that the model have some unwanted behavior. Especially in low brightness image, the model trained to systematically predict the image as conform, and the same thing for the high blurred image. And for the high brightness image, we have a fall of the prediction confidence for the conform class. So we can say from such analysis that our model can only operate in a specific operating zone with a medium brightness and very small blur value. But if we want to come back from the transformation event to a more usable indicator, here the teams which done such work have found a limit because ODD condition measure of the quantifier show a strong variability for transformation level of the generator. There is some solution which are to better filter data or to build more specific quantifier and generator which can be more adapted to the data, the operational data, and that's the purpose of the modular design of MOODD can face such specific challenge related to operational data. So you can have more information on the documentation link provided here, and thanks for your attention.